Today's lesson is about the concept of half-life. This is a very important idea in nuclear chemistry and nuclear science. And so half-life is defined as the amount of time it takes for half of a radioactive isotope to decay. Now, what this is telling us is that when you have radioactive isotopes that are decaying into some other element or some other object, it doesn't decay at a very stable rate. It decays what's called at an exponential rate. Now here's an example. Some isotopes have a very short half-life. Astatine-218, for example, has a half-life of 1.6 seconds, and so it decays very, very quickly. Polonium-210, on the other hand, a notoriously toxic substance, has a half-life that's a little bit longer, about 138 days, so on the order of about 4.5 months. Carbon-14, on the other hand, this is a radioactive isotope found in every living thing, everything that is alive or has been alive, has a half-life of about 5,700 years. On the other hand, there are other isotopes that have extremely long half-lives. Uranium-238, for example, takes 4.5 billion years for half of its atoms to decay into something else. It decays very, very slowly. It's not so slow that we say it's stable. It's still decaying, but it's just decaying at an extremely slow rate. Now, how does half-life work? Well, let's examine the decay of a certain isotope here. Let's say that this isotope is radioactive, and we start with 100 grams of it. And let's suppose that it has a half-life of 15 days. Well, if that's the case, then after 15 days, according to this idea of half-life, that means half of it is going to be left, and so you'll be left with 50 grams. That's half of 100. Now, what about the next 15 days, after a total of 30 days has passed? Does that mean we'll have zero? Will all the rest of it decay? No, it just gets cut in half again. So after 30 days, that's another 15 days, a second half-life, we have 25 grams left. That's a quarter of the original. Now, if we let another 15 days pass, we'll have half of the 25. So we'll have 12.5 grams. So that's 1/8 of the original amount. And this can go on and on and on. If we have another 15 days, then half of 12.5 will be left. So that's 6.25 grams. So it's 1/16 of the original amount. And we can basically keep on and doing this for a very, very long time. So those of you who are more mathematically inclined might notice that after one half-life, the fraction that's left is equal to 2 to the -1 power. And after two half-lives, the fraction that's left is equal to 2 to the -2 power. After 3 half-lives, it's 2 to the -3rd. After 4 half-lives, it's 2 to the -4th. And so you can see a pattern here. If you're mathematically oriented, well, after 25 half-lives, the fraction that'll be left would be 2 times 10 to the, or rather 2 to the -25th power. So you could find out what that fraction is and multiply it by the original and decide how much is left. In our class, though, most of our calculations will be much simpler than that. Let's try a few problems and see what we're talking about. In this problem, it says that a radioactive isotope has a half-life of 3 days. If we begin with a mass of 50 grams, how much of the isotope will be left after 12 days? I strongly recommend to students in first-year chemistry that instead of trying to turn this into a mathematical equation, which is possible, the best thing to do is just to set up a chart, set up a diagram that shows how this is decaying. So what I like to encourage students to do is we start with 50 grams. We realize what we start with, so 50 grams, and we always start with times 0. And so that means at times 0 days, we have 50 grams. And then we start counting based upon our half-lives. So the problem says that the half-life is 3 days. And so that means that after 3 days, the amount that's left is half of 50. That's 25 grams. Well, another half-life will pass, so that's a total of 6 days, 3 more days. And so the amount that's left will be half of 25. So that's 12.5 grams. Now another 3 days will pass, so that's 3 plus 6, which is 9 days. And so we'll have half of 12.5, which is 6.25 grams. And then another 3 days will pass, and that's a total of 12 days. And then the amount that's left will be half of that, half of 6.25, which is 3.125 grams. And lo and behold, that's what the question is asking about. It says how much will be left after 12 days, and so we can say the answer is 3.125 grams. Let's try another example. This one is a little bit different. This one says an isotope has a half-life of 18 minutes. How long will it take for the amount of the isotope to drop from 70 grams to 17.5 grams? Well, once again, we do the problem the same way. We start with a diagram. We start with 70 grams, because that's what's mentioned to us at time 0. And so we always start at time 0. So at 70, we have 70 grams at 0 minutes. And then if the half-life is 18 minutes, that means that after 18 minutes, we've dropped to half of 70, which is 35 grams. Now another half-life would be another 18 minutes, so 18 plus 18 is 36 minutes. And in that half-life, it will drop to half of 35, which is, I believe, 17.5 grams. And lo and behold, that's what the question is asking about too. How long will it take to drop to 17.5 grams? And so that's the answer. It's 36 minutes. And so making a little chart, a diagram here, can help you to solve these half-life problems. Here's another example. It says an isotope has a half-life of 12 minutes. How long will it take for the amount of the isotope to drop from 80 grams to 10 grams? So once again, we're going to make a diagram. We always start with time 0. Our original amount is 80 grams. So we start with 80 grams at time 0. Our unit seems to be minutes this time, so we'll say 0 minutes. And this time, what is the half-life? Well, it says the half-life is 12 minutes. So that means that after 12 minutes, how much is left? Well, whatever half of 80 is, which is 40 grams. If we allow another 12 minutes to pass, another half-life, that's 24 minutes. 12 plus 12 is 24. And so we're left with half of 40 grams, which is 20 grams. And then we have another 12 minutes, another half-life. 12 plus 24 is 36 minutes this time. And half of 10, or rather half of 20, is 10 grams. And if you look at the problem, you'll see that that's what the question is asking about. How long will it take to drop to 10 grams? And so it looks like the answer is 36 minutes. And so the diagram method of solving half-life problems is very effective, as you can see. Let's try one more example. It's perhaps a bit more challenging. This one says we start with 20 grams of a radioactive isotope. If it takes 33 minutes for the amount to drop to 2.5 grams, how long is the half-life of the isotope? Now, this one's harder because we're used to having the amount or the length of the half-life to work with. But this time we don't have that, so we have to be a little bit more ingenious in the way that we write our diagram. Now, we're still going to start with 20 grams. We start with 20 grams. And so I put 20 grams here. And we know that that's times 0. And it looks like we're dealing with the unit of minutes here. So we'll say 0 minutes. But this time, it says that we don't know how long the half-life is. We have to calculate that. So I don't know how long it's going to take to get to this point, but I do know that after the first half-life, however long it is, we're going to have half of 20, aren't we? And half of 20 is 10. So at least we know that much. And then after the next half-life, how much will we have left? Well, half of 10, which will be 5 grams. And after the next half-life, we're down to half of 5, which is 2.5 grams. But take a look at the problem. It says it will take 33 minutes for the amount to drop to 2.5 grams. So we know this much. We know that at 33 minutes, we're down to 2.5 grams. Now, how many half-lives have passed? I hope you didn't say 4. Because if you look at the number of half-lives that passed, remember, 20 grams is 0 minutes. We have one half-life here. The second half-life is that jump. And the third half-life is that jump. So really, only 3 half-lives. And so 33 minutes is the same as 3 half-lives. So let's calculate that. If 33 minutes is the same as 3 half-lives, what is the length of 1 half-life? Well, whatever 33 divided by 3 is. Hopefully you realize that that is 11 minutes per half-life. And so the answer to the question is that the half-life is 11 minutes long. So once again, we've worked several problems in which we've used a diagram or chart here to solve half-life problems.